Welcome to your Day 1 orientation, site engineers. We're jumping right into the deep end today, breaking down the absolute foundations of concrete, steel, and high-rise quality control. Look, if you're going to be managing massive construction projects, you can't just look at the big picture. You need to know exactly what's happening at the microscopic and structural levels. Think of this explainer as your essential field guide to mastering the materials that literally build our world. All right, let's get into it.
Here is our game plan for today's briefing. We're starting with the essential materials on site, looking at how we combine concrete and steel, comparing nominal versus design mixes, and finally, diving into the strict lab testing and quality control required for high-rises. Starting with Section 1, Essential Materials on Site. These are your building blocks. Because before we build absolutely anything, you need to know exactly what's spinning in that mixer drum.
Let's look at the basic everyday recipe. You've got cement, which is your crucial binder, basically the glue of the whole operation. That cement pulls together your coarse aggregate, which you probably know as crushed stone or jelly, and your fine aggregate, which is the sand. You add water to activate that cement binder, and boom, you get concrete. Seems super simple, right? But mastering the exact ratios of these four ingredients, that is the entire foundation of civil engineering.
Now, concrete by itself just isn't enough for true structural integrity. And that brings us to a term you're going to be using all the time, RCC, or Reinforced Cements Concrete. This is where we embed steel reinforcing bars, rebars, straight into the wet concrete. Why bother? Because while concrete is incredibly tough, it has a fatal flaw when it comes to pulling forces, also known as tension. RCC fixes this by giving the concrete a literal steel skeleton.
Which perfectly sets up Section 2, Combining Concrete and Steel, and why rebar is absolutely non-negotiable in modern construction.
Think about the actual mechanics of a building under a heavy load. Concrete is an absolute beast under downward compression. You can push down on it with a massive amount of weight. But what happens when a concrete slab bends? It introduces tensile forces. The top compresses together, but the bottom pulls apart. Without steel in there, those tensile forces will literally rip the bottom of the concrete wide open, leading to catastrophic cracking and total failure.
So, the magic really happens when you understand the synergy between these two materials. They are the perfect team. Concrete takes the crushing compressive loads, and steel steps up to handle the pulling tensile loads, since steel is strong in both. But here is the truly mind-blowing fact that makes this entire partnership possible in the first place. Their coefficients of thermal expansion are almost perfectly identical. Steel expands at about 1.1, and concrete at 1.2 times 10 to the negative fifth per degree Celsius. That means when the hot sun beats down on a bridge, the steel and concrete expand and contract together instead of tearing each other apart. Add in the ductile, flexible nature of steel, plus those textured ribs on the rebar that lock firmly into the concrete, and you've got a flawless structural marriage.
Let's move on to Section 3, Understanding Nominal Mixes. We can think of this as the fixed recipe approach to mixing concrete on site.
To really wrap your head around a nominal mix, imagine a fixed-rate market stall. You know the ones, no bargaining allowed whatsoever. The ingredient proportions in a nominal mix are strictly set in stone. It completely ignores local conditions. You don't haggle, you don't tweak things, you just blindly follow the fixed recipe.
So, what does that fixed rate actually look like on the ground? For your standard lower-grade mixes like M10, M15, or M20, the ratios are entirely predefined. Take M20 for example. It's exactly 1 part cement, 1.5 parts sand, and 3 parts aggregate. We get this mix using basic volumetric batching, just scooping and measuring by volume. But here's the catch. There is zero quality control testing. We aren't testing the individual materials, we don't run workability slump tests, and we definitely don't crush cubes in a lab to verify the compressive strength. We just assume that because we followed the recipe, the strength is magically there. Now, for a small residential walkway, sure, that might be fine. But for massive structures, no way.
Which leads us to Section 4, High-Rise Design Mixes. When you're building a skyscraper, simply assuming your concrete is strong enough is literally a recipe for disaster. We have to custom engineer the mix. Seeing these two side by side really shows you the leap in engineering. While nominal mixes lean on simple volume and blind faith, design mixes are a whole different beast. First off, we use precise weight batching, not volume. Secondly, the ratios are not fixed. They fluctuate based on the specific local materials you're using and are meticulously engineered using the IS 10262 2019 codebook. Plus, we don't just stick to the basic 4 ingredients. We bring in chemical additives, like plasticizers to cut down on water while keeping the flow smooth.
Or we add fly ash and GGBS to completely alter the concrete's core properties. And most importantly, we assume absolutely nothing. Everything is backed by strict lab verification.
And that brings us to our final and arguably most critical topic for high-rises, Section 5, Quality Control and Testing. This is how we actually verify structural integrity.
This right here is QC in action. We take the exact engineered mix that we're planning to pump 30 stories into the sky, and we cast it into precise 150mm steel molds. We pour it in layers, properly tamping it down to force out any trapped air voids, preparing it for absolute, undeniable verification in the lab.
If you're on a high-rise project using a design mix, specifically for grades M25, M30, M40, and up, isn't just a good idea, it's mandatory. Your main job as a site engineer is enforcing this strict quality control. Every single ingredient is tested individually before it even touches the mixer. Then, once it's mixed, you have to run a step-by-step slump test. You fill a standard metallic cone in 3 separate layers, tamping each layer exactly 25 times. You carefully lift the cone straight up and measure exactly how many millimeters the wet concrete drops, or slumps, to verify its flow and workability. After that, for those steel cubes we cast earlier, we cure them in water for up to 28 days. Then they go into a hydraulic compression testing machine. That machine applies a slow, gradual load until the concrete cube systematically cracks and fails, which lets us calculate its exact ultimate compressive strength. With a design mix, your required strength is completely justified by hard data and rigorous lab tests. No assumptions allowed.
So, apprentices, as we wrap up this explainer, I want to leave you with one final thought. When you step on your first high-rise site tomorrow morning, are you just going to see gray sludge tumbling out of a cement truck? Or will you look at that concrete and know exactly how its chemical binders, its perfectly paired steel rebars, and its rigorously engineered lab tests are all working together to literally hold up the weight of the sky? The safety of tomorrow's cities rests completely on your understanding of these fundamentals today. Thanks for joining me on this site briefing, and keep learning.